Hello everyone. So welcome to the third lecture of second unit. Uh, we have already studied about the zeroth law, first law of thermodynamics, and several definitions till now. Right now, we have in the last lecture we have also seen some applications of first law of thermodynamics. Now we will move to our next topic, which is very important, and of course it is also using first law of thermodynamics, but this is important because it is giving the principle of any heat engine. So this was developed by a scientist, Carnot, and it was proposed as a theoretical engine. Okay, so today's lecture topic is related to that Carnot engine and Carnot cycle. Okay, so here is the objective of today's lecture. This is to learn Carnot's engine and cycle. The outcome of the lecture, after you attend this lecture, you will be able to learn about the reversible and irreversible process. First, we will define what we call reversible and irreversible. What is the properties and what is the conditions? What are the conditions they should follow to call reversible or irreversible process? Okay. Then second point, you will learn about the working principle and the definition of heat engine. This will be in general, and then we will move to the proposed Carnot engine and Carnot cycle, and will be able to derive the efficiency of this engine. You will be able to learn how to calculate the total work done by this engine. So you will be able to understand how our daily life engines work. Okay, to achieve these objectives, the lecture is divided into these several contents. The first one is reversible and irreversible process. We will define it, and we will define the conditions for each of the process. Then second, we will learn about heat engine. The third one is about efficiency of heat engine. We will calculate the efficiency of normal heat engine, and then we will introduce Carnot's ideal heat engine. Here it is ideal because this is the theoretical concept only. Actually, in principle, it can be possible, but in practical life, it is not possible to design this kind of ideal heat engine. So there is always the efficiency should be less than 100. There is always a loss of heat. But according to Carnot, this theoretical engine, there should be no loss of heat, no loss of energy. Now the next one is Carnot cycle, and in this topic we will calculate the total work done in Carnot cycle and the efficiency of Carnot engine. Here are the list of reference books. These all books are very simple and easy written. The third book is from Brijlal and N. Subramaniam, and it is very good to consult if you want to learn the basics of thermodynamics. For all the topics, it is very simply written. Okay, so let us start. First topic of today's lecture: reversible and irreversible process. So definitely any process we can define only in two way. Either it will go to some point and come back to the initial point, right? That is actually, in common sense, if we learn, that is the reversible process, right? Irreversible is what? If we go to some point and it is not possible to go back to the initial point, then it is irreversible. According to thermodynamic point, we can define it as a reversible process is the process which can be retraced or which can be coming back in the opposite direction by changing the external conditions. Important word is infinitesimally. That means it should be extremely slow. Okay, so it we can call it quasi-statical also. That means it looks like static, but actually the reaction is processing. So we cannot see if the reaction is processing by our eyes or by the experience, but there are some changes which is taking place. Okay, for this, if for example, if heat is absorbed, we can understand this reversible process by an example. If for example we are giving some heat to any substance in this direction, for example, from here to here, okay, the same quantity of heat should be released if from here to here the heat is absorbed by the substance, the same amount of heat should be released in the reverse process. If the substance is coming from this state to this state, the same amount of heat should be released. Okay. And in terms of work, if some work is done from here to here, the same work, if the work is done by substance in this process, then the same work should be done on the substance in the reverse process. So that means what we are supplying, we are getting the same amount. Okay, either it is in heat terms or in work terms. So that means there is no wastage of energy in the reversible process. Okay, if there is any loss of heat due to any phenomena such as friction, radiation, or conduction, then the process cannot be reversible, because we cannot achieve the same amount of heat in the reverse process. The second condition, if these changes from this state to this state, if this change is very fast, the rate of reaction is very fast, in that case also the process cannot be reversible, because if it is very fast, there must be some heat loss in that process because of kinetic limitations. Okay. So here are, on the basis of this definition, we can define some conditions for the reversibility. Okay, how these are, we will see point by point. The first point is the pressure and temperature of the working substance should not be differ appreciably from those of surrounding. You know, all the systems are surrounded by some surroundings. Actually, these surroundings is around every system, right? So the temperature and pressure condition of this system should not be too much different from its surrounding at any stage of operation. The engine, if this is working for the expansion or compression, the temperature and pressure value should be somehow similar, or that should not be different by a large amount. Okay. The second point is all the process in the operation cycle should be extremely slow. The rate of reaction or the rate of process should be very slow, and that's why we call it infinitesimally. Or the process should be quasi-static. Quasi-static means the process which looks static, but in actual it is not static. Every time there are some changes taking place. Okay. The third one is the working parts of the engine must be completely free from friction. Of course, if there will be some friction, the machine or any system has to work against that friction, and during that friction, during that work, it will lose some energy to oppose that friction. That means the working part should be, of course, friction free, right? The fourth point is there should not be any loss due to conduction, convection, and radiation, or any other process during the cycle of operation. Okay. Now, because these conditions are actually not only difficult, but somehow we can say these are impossible to achieve in our practical life. So that means completely reversible process is only phenomenal. It is not possible to get a reversible process in practice. It is only an ideal case. Okay. In all the practical processes, in actual processes, there is always some loss of energy due to any of the reaction, any of the mechanism like conduction, convection, or radiation. Okay. Then let us go to irreversible process. It is just opposite to reversible process. And actually, in nature, if we look on any process, all the processes are irreversible. Why these are so? There are two reasons. The first one is the condition for thermodynamic equilibrium. That means mechanical, thermal, or chemical equilibrium cannot be satisfied, because any natural process, or we can call any spontaneous process, does not happen quasi-statically. It cannot happen infinitesimally. So that's why it is irreversible. Okay. The second one is dissipative effect such as friction, viscosity, inelasticity, electric resistance, eddy formation. These kind of dissipative effects always exist with all of the natural process, all of the practical processes. Here are some examples. For example, if we allow any gas to expand spontaneously into an evacuated, if for example if we take some particular amount of gas in one box, okay, if we are taking in the box and we open it immediately, what will happen? This gas will be spread out throughout the room, okay, and it is not possible to bring all the gas molecules back into this box. That means this is irreversible process. Or if we take an example, if we take one simple rod, iron rod or any metal rod, of which one end is very hot and another end is cold. So the heat flow due to conduction, due to this temperature gradient, is irreversible process, because due to conduction, if we make this end hot, this end is cold, after some time the total rod will be at the same temperature. Heat will flow from this end to this end, and that means we cannot bring it back to the original condition. We cannot cold one end and hot other end, right? So this is also a irreversible process. Okay, now we already understand that the ideal reversible process cannot happen in our practice life, in our practical life. So why it is important? Why we are considering these? We should leave it and we should consider only irreversible process. But for the thermodynamic point of view, for the thermodynamic calculations, it is important to consider the ideal conditions, because we cannot track the practical conditions for the actual calculations. So for thermodynamics, it is very important, because they can be handled analytically. We can use them for a particular case for the calculation, and of course we can always add some error due to practical things. We can calculate some other parameters and then we can modify it, but initially we should calculate ideally. Okay, here is the next topic. We will move to Carnot's ideal heat engine. Before going to the Carnot's ideal heat engine, we will understand what is heat engine. So heat engine is nothing but actually it is just a practical machine which converts heat into mechanical energy, heat into mechanical work. That is known as heat engine. Okay, now what they do absorb heat at high temperature and converts a part of this energy into work, and rest of the part of that energy, of that heat, they transfer to the some system at low temperature. Okay, so they absorb at high temperature, they do some work and release the remaining heat at low temperature. Okay, in the process of this working, in the process of heat engine working, the working substance can go through several changes for their temperature, for their pressure, for their volume, but after completing the cycle they should return back to the initial state. Okay, the complete changes through which the working substance undergoes from its initial state and back to starting state again. So for example, if we start from here, we go to here and come back this. So this complete is one cycle. We call it one cycle of operation for that heat engine. Okay, now we will define what is the deficiency, what is the efficiency of heat engine. Okay, so how to define? The efficiency of a heat engine is defined as the ratio of the mechanical work and the heat supplied or heat absorbed by the engine in one cycle of operation. That is known as the efficiency of heat engine. If we represent it in mathematical terms, we can assume that, for example, heat engine absorbs some heat Q1 at high temperature and release heat Q2 at low temperature, right? So how will we calculate the work? The difference of this and this heat, Q1 minus Q2, right? That will be the mechanical work. So we have written here Q1 minus Q2 divide by absorbed heat. So that is Q1. So efficiency is equals to Q1 minus Q2 upon Q1. Okay. So from this expression, it is clear that this quantity Q1 minus Q2 is always less than Q1, and definitely because we are subtracting some finite quantity from the initial amount, which is here also. So that means this amount will always be less than the absorbed heat, and that's why the value of eta will always be less than 1. That means the efficiency will never be possible as 100%. Any heat engine cannot deliver 100% efficiency. It will always be less than 100, and for the practical life, we can achieve 90 to 95% of efficiency if we can control the conditions very nicely. Okay. Now we will see the design of Carnot's ideal heat engine. Here are some parts. So we will see one by one. We will see some history first. So this engine actually was proposed. This was a theoretical engine, as I told you before also. This is a theoretical engine, and it was proposed by a French engineer, Sadi Carnot, in 1824. This engine was considered to be free from all the practical imperfections. There is no imperfections in the design of this heat engine. That means there should be no friction. There should be the maximum efficiency, and that's why it is called as ideal heat engine. Now we will see the what it constitutes. So the first part is cylinder. We will see in the figure here, this cylinder is looks like this, and the walls of this is completely insulating, so that there is no heat loss or there is no heat exchange with the surroundings. The system should be completely isolated from the walls, and this piston is also completely insulated, so the heat cannot be transferred from this part. And again, the second point for the piston is this piston should be frictionless. So whenever we move up and down, there should be no loss of energy. So this is only ideally possible. That's why we call it ideal engine. Important point here is that the base is completely conducting. Okay, this can allow the heat from the surrounding. So this is the important characteristic of cylinder. The second thing is the source. The source is what? This is a kind of reservoir which is maintained at temperature T1. We are considering the temperature of this T1, and the other walls are completely insulating, so there should be no loss of energy from the wall side or the bottom side. Only the top surface is the conducting surface where the heat can be exchanged with the surroundings. Okay. The third thing is one more important point here, because this source, because we are maintaining the temperature at T1, so that means the heat capacity of the substance is infinite, so that it can maintain the temperature whatever the heat can be supplied to it. If we supply any amount of heat, there should be no change of temperature, no change of temperature of this source. That is important characteristic. The next part is heat insulating stand. Heat insulating stand is completely insulated. All the walls are completely insulated. There is no temperature, there is nothing. We can control it for the adiabatic processes. For example, if we put this cylinder here, it will not exchange any heat with this, so there will be no heat change between the process. And for that, we are using as a adiabatic process, either adiabatic compression or adiabatic expansion. Okay, the last part of the heat engine is sink. What is sink? This is again a kind of reservoir. Here it was at temperature T1. this is at temperature T2, and the important condition for the heat engine is the temperature of source should be greater than the temperature of sink. So if we denote it T2, then T1 should always be greater than T2. Again, the design of sink is very similar to the source. All the three walls, that means the walls are completely insulating, the bottom is completely insulating, only the top surface is conducting, so that it can transfer, it can exchange the heat with the cylinder. Okay, here we are assuming that the total amount of working cement substance is 1 mole of gas. We are considering here that 1 mole of gas is inside the cylinder. Okay, so here everything is written whatever I have explained it with the image. Now we will see how this Carnot engine works, and we termed it as Carnot cycle because it is starting from this point. For example, it is going to some part, then here and coming back to the original point. Okay, now in order to obtain a continuous supply of work, the working substance is subjected to the following cycle of quasi-static operations known as Carnot cycle, whatever I told you. So for example, this is the starting point, the A point we are considering. It will go to first isothermal expansion, then again adiabatic expansion and isothermal compression, and coming back to point A by adiabatic compression. So we will see each of the part one by one. There are four different processes which complete one Carnot cycle. We will calculate the work done in each process one by one. So for the first process, let us assume that it starts from A and reach to B. So for this, let us assume that the cylinder is first placed on the source. So if you please recall this image, let us assume that first process is done by placing this cylinder at source so that the heat can be exchanged between these two. Okay, so for that, let us consider that the gas inside the cylinder take the heat from source. It can supply the heat to the gas, and that amount we are considering that Q1 is the amount of heat that is taken by the substance from the source, and the temperature is reached to T1, which is similar to the temperature of the source, right? Source temperature was T1, we assume already. So because we are allowing these process very slowly, and we are saying that if it is happening very slowly, what will happen? Because of heat transfer, the temperature will rise, and what will happen? The piston will go up. That means the gas inside the cylinder will expand. So that is known as isothermal expansion, because the temperature is maintained at T1 because of the temperature of source. Okay, now at the same time, what is happening for any process, if we consider, we are not assuming any source or anything, if we take some gas and allow the expansion of that gas, what will happen? When the gas is expanded, the temperature always try to fall down. Okay, but because of the presence of source, this temperature remains constant, and that's why we are calling that this expansion is taking place isothermally. The temperature remains constant, so that's why we are calling isothermal expansion because of the source. Now since the temperature is constant, we are assuming that these two values are constant for this process, because the amount of heat is constant Q1 and the temperature is T1. Now the coordinates for these starting point and the final point, let us assume that the P1 and B1 was the pressure and volume for the starting state, and for the final state it is P2, B2. So the total work from here to here will be given by Q1 equals to, because we have supplied the heat Q1, that will equal to W1, and that can be written as integral within the limits B1 to B2 of P into dV. dW is always given by P dV. So because we are changing from V1 to V2, we are integrating within the limits of V1 to V2. If we integrate, before integrating, we can change P to different terms by using ideal gas equation. What ideal gas equation is? PV equals to RT. So P will be equals to RT upon V. And if we put this value here, RT upon V into dV. R and T is constant here because the temperature is always maintained as T1. So we can write R into T1, and if we integrate it, dV upon V, that will be log V. And if we put the limits, it will become log V2 minus log V1. If we solve this, we can collectively write log V2 upon V1. So the final expression of the work done in this cycle, in this process, will be equals to RT1 log V2 upon V1. And if we look at on the graph, in terms of pressure volume graph, we can write it is equal to the area of AB GEA. Okay, so this is the area which can represent the work done in this process. Okay, this is because expansion, so work is done by the work done by substance. Okay, now here we are again doing the second process. For this process, we are keeping the cylinder at the insulating stand. So it was earlier at the source. If we recall again the figure, you can see here in the first process, the cylinder was kept at source. Now in the second process, this cylinder is kept at stand. Okay. Now if it is at stand, what will happen? We can see from here what will happen, because there is no heat exchange and the temperature is of course different of the stand. So what will happen? Slowly the temperature of that gas will be going down. The temperature will be changed. We allow this until a temperature of sink. I mean the temperature of the gas fall down up to the point which is equal to the temperature of the sink. Okay, that is T2. So we allow this when the temperature will this is adiabatic expansion. I'm telling it wrong. Actually, the cylinder is removed from the source and placed on the insulating stand. And because this is expansion, we are actually allowing this cylinder to expand. So still the piston is going up and going to adiabatic expansion, because during this process there is no heat exchange. So that means it will work externally. There will be some external work until the temperature will fall down to T2. Okay, this process is adiabatic expansion, and this operation is represented in this cycle from B to C. Okay, now we are considering the coordinates of the starting point as P2 and V2, and the final point as P3 and V3. Here remember, the temperature is also changing. Temperature is changing from T1 to this point as T2, because there is no heat exchange now, so the temperature will fall down. If the temperature will fall down, we are considering that the new temperature is equal to that of sink temperature, that is T2. In this part, there is no heat transfer, so the work will be without heat transfer, and that will be given by, again the same thing, W2 equals to the integration within limits V2 to V3 of P into dV. So P into dV. Now we can write it from adiabatic expansion. We have already derived some equation, and that was given by PV to the power gamma equals to constant. Here we are considering that constant is given by K. So if we replace the value of P by this equation, it will become K upon V to the power gamma. So K is constant, so it will taken out from the integration sign, and it will become K into integration V to V3 in of dV upon V to the power gamma. If we integrate this, we will get the final expression as KV3 to the power 1 minus gamma minus kV to the power 1 minus gamma upon 1 minus gamma. Okay. Now, if we consider this again, we can write this P3V3 minus P2V2. Again, we are considering the same equation, but for the two different states. Here, PV to the power gamma equals to constant, so we can write P2V to the power gamma equals to P3V3 to the power gamma equals to K. So we are replacing this with this equation, and it will become P3V3 minus P2V2 upon 1 minus gamma. Here this can again be replaced by the ideal gas equation. It will become PV equals to RT. So it will become, because at point 3, P3V3 is the coordinate of C point, and at C point the temperature is T2. So for that we can replace it as RT2 minus, if we write for P2V2, the temperature is T1. So we can write minus RT1 upon 1 minus gamma will be as it is. That will be equals to R into T1 minus T2 upon gamma minus 1. And that will be equals to the area BCHGB on the PV curve. Okay. Now let us go to the third process. For the third process, we will again pick the cylinder, and from the insulating state we will transfer it to the sink. Okay, now it will be placed on the sink, which is at temperature T2. Now since the top of sink is the conducting surface and the bottom of the cylinder is also conducting surface, so there will be some heat exchange between them. Now since the temperature is at T2, even if it transfers some heat to the sink, or it will try to change the temperature, but what will happen, because the sink is at T2 temperature and the heat capacity of sink is infinite, there will be no change in T2. Now what we are doing, we are trying to compress the gas, and if we try to compress the gas by pulling the piston down, what will happen? During the compression, the temperature of gas will try to increase, but due to that increase it will transfer the heat immediately to the sink, and that's why the temperature of the system will remain same. Now what is the temperature of that system? It will remain at T2 because the sink temperature is T2. Okay, so this is again at isothermal condition because we are keeping the temperature constant. So this, during the isothermal compression, we are considering that this state goes from C to D, and the coordinates are changing from P3V3 to P4V4. In this process, the work will be calculated in the same way as we calculated in the isothermal expansion, right? The only point will be here that Q2 is equal to, here we are transferring the heat Q2 from the cylinder to sink. In the first process, we were transferring the heat from source to cylinder, Q1 heat, and here Q2 heat is released from the cylinder to sink, right? So the work done will be equals to W3, and that will be from B3 to B4 limits of integration of P into dV. Again we will change because this is isothermal condition, and for that we can consider PV equals to RT, that is constant. So we can replace this P equals to RT upon B, and here the temperature is T2, so we are writing RT2 upon B. If we integrate this dV upon B, it will change to log V, and because the limits are B3 to B4, it will become RT2 log B4 upon B3. Now we can change the sign of this. It will become minus RT2 log B3 upon B4. We are just changing the order here, and this will be equals to the area of CDFHC. That will be the work done on the PV curve. The last process of this Carnot cycle will be just opposite to the adiabatic expansion. Now we are doing the compression process, and for this, because this is adiabatic, we are again placing our cylinder to the insulating stand. Okay, and we will try to compress to increase the temperature of that cylinder, of that working substance, or we can call the gas inside the cylinder. If we compress it, the temperature will again increase from T2 to T1. We will allow that time so that it can reach from T2 to T1. So the new coordinates of the points will be P4, B4 and T2 at this point. Now it is coming back to the initial state, and the temperature, pressure, volume values are T1, P1, B1. Okay. During this consideration, the work will be actually the same as that of this. That will be equals to W4 equals to B4 to B1 into PdV. And again, we can calculate the same way we have calculated for adiabatic expansion. We will again use the same equation, PV to the power gamma equals to constant, and from there what we have calculated here, R into T1 minus T2 upon gamma minus 1, we will calculate the same way. It will be minus R T1 minus T2 upon gamma minus 1, and that will be given by this area ADFEA. That is the work done on our PV curve. Right now, because we have all the works done in different processes, in this process, third process and fourth process, so the total work done will be W1 plus W2 plus W3 plus W4. That's what we have written here. The net work done by the engine per cycle is equals to W1 plus W2 plus W3 plus W4. But we can see here that the value of this W4 is exactly equal in terms of its magnitude, but with the opposite sign, because one is expansion and another one is compression. So that's why they will cancel out each other, and that will be equals to W2 equals to minus W4. So this will be cancelled. The net work will be remaining as W1 plus W3, and that will be equals to area ABCDA. What is that area? Because the total process is this, so the total area will be ABCDA. This will be the work done during this reversible process. Okay. So one thing is work. Second thing is we have supplied some amount of heat and we have released some amount of heat. So that is the net amount of heat is Q1 minus Q2. So that is the net amount of absorbed heat by gas per cycle is equals to Q1 minus Q2, and that should be equals to the net work done. So that's why we can write the cyclic process will give net heat absorbed equals to net work done. And if we put the values of this, it will become Q1 minus Q2 is the net heat absorbed equals to net work done is W1 plus W3. Putting the values of this, we will get RT1 into log V2 upon V1 minus RT2 into log V3 upon V4. Let us assume this as equation number 5. If we see again now, we will take the consideration of the adiabatic processes. We have calculated some equations between P and B, P and T, and B and T. We will consider it now here. Now look at the figure and we will find that A and D are on the same adiabatic process, right? They are lying on the same curve. Similarly, B and C are also lying on the same point. So that means this is adiabatic process. And for adiabatic process, we know that T V to the power gamma minus 1 is given equals to constant. So for that we can write what? For this one, T1 V1 to the power gamma minus 1 will be equals to T2 V4 to the power gamma minus 1, because here the temperature was T2 but the volume was V4. So we have written this T1 V1 to the power gamma minus 1 equals to T2 V4 to the power gamma minus 1. If we rearrange this, we will get T2 upon T1 equals to V1 upon V4 to the power gamma minus. Let us assume is as equation 6. This is for the curve AD. Right now we will consider curve BC. It is again the adiabatic process, so we can use the same equation, but here the terms are different. What? Because here the temperature is T, the volume is V2, so we can write T1 V2 to the power gamma minus 1. Here the temperature is T2 and the volume is V3, so we can write T2 V3 to the power gamma minus 1. If we rearrange it in the same way as we have done here, it will give T2 upon T1 equals to V2 upon V3 to the power gamma minus 1. That is our equation number 7. If we compare these two equations, since left hand side is very similar for each equation, the right hand side should also be equal. That means we will get V1 upon V4 equals to V2 upon V3, or we can rearrange it and find that V2 upon V1 equals to V3 upon V4. Now if we put this value in our equation 5, see in equation 5 it was V2 upon V1 and V3 upon V4. So what we get, we will change the term here and here, V2 upon V1 and V2 upon V1. Now since this term is common from the both sides, R is common, we can take it out, R into T1 minus T2 log of V2 upon V1. So this is total work done in a complete Carnot cycle. Okay, this is the expression for work. Now we will calculate the efficiency, and efficiency of any engine is given by the difference of heat absorbed and heat given, that is equals to the work done. So that is Q1 minus Q2 upon Q1, the heat absorbed by the system. We already know the value of this, we have just now calculated from here. Q1 minus Q2 is equals to this one. So we have written here R T1 minus T2 into log V2 upon V1, and we know the value of Q1 also, we have calculated it in the first cycle, and that is equals to RT1 log V2 upon V1. If we calculate, we simplify it, we get eta equals to T1 minus T2 upon T1, or eta equals to 1 minus T2 upon T1. That is our final expression for the calculation of efficiency of any Carnot engine. So from this equation, we can conclude that the efficiency depends only on the temperature of source and sink. It is never related to the nature of working substance. Whatever gas we take, whatever working substance we take, it will only depend, the efficiency only depend on the source and sink temperature. And that should always be less than 1. Why? Because this value should always be a finite quantity, and that means it will be less than 1. Efficiency can be 1. From this equation we can get second conclusion, that efficiency can be 1 only in the case when T1 will be equals to T2. That will it will not be 1, it will be 0 in that case. For efficiency to be 1, it should be possible only when the T2 value should be 0. T2 value means the sink temperature is at absolute 0 temperature, but we know that it is impossible to achieve absolute 0 temperature in the practical life. So that is in fact not possible, and that's why the efficiency of any heat engine is never be possible to be 100%. It cannot change the complete heat energy to mechanical energy. Okay, now the third case is the efficiency will be minimum, or minimum means it will be 0 when the value of T2 upon T1 become 1, and when it will become 1, when the temperature of source and sink should be same. So T1 equals to T2 will make efficiency 0. If the temperature of source and sink will be same, the engine cannot work, engine will not work. Okay, now regarding this Carnot engine, we can consider one more point, because we started from point A and we started to isothermal expansion, then we allow adiabatic expansion, after that we allow isothermal compression, and finally adiabatic compression. If we reverse it, first we do allow adiabatic compression, isothermal compression, and then adiabatic expansion and isothermal expansion, right? If it is in the reverse direction, it can also be operated in the same way. But now what we have studied, it was as a heat engine. If we do it in the reverse process, it will work as refrigerator. The heat Q2 will be taken from the sink, and external work will be done on the substance, on the gas, and then the heat Q1 will be released to the source at high temperature, and that is the principle of our refrigerator. Okay, so that is all about the Carnot cycle. Now, to understand what we have learned today, we will do some quiz. Here are some questions which you need to answer. So the first question for today's quiz is, in Carnot cycle, the first step is isothermal expansion. Second option is isothermal compression. The third one is adiabatic expansion, or fourth option is adiabatic compression. So of course we started from point A and we allow because we put it first at the source, and that time we allow it for the expansion, and because source and piston can transfer the heat, that was at isothermal, so it was isothermal expansion. So the right answer for this question will be answer A, isothermal expansion. Second is, an engine works between the temperature 30 and 300 Kelvin. What will be the efficiency? So we know the formula for efficiency, eta equals to 1 minus T2 upon T1. If we calculate it from that value, we will get the answer C, that is 90%. Okay. The third question is, a reversible heat engine can be 100% efficient if the temperature of sink is less than that of source, equal to that of source, 0 degree C, or 0 Kelvin. So we have seen the efficiency formula, eta equals to 1 minus T2 upon T1. So what is the temperature of sink? That is T2. So 1 minus T2 upon T1, when it will be 1, when this term will be 0. And for that term to be 0, we need a condition that T2 should be 0 Kelvin. The absolute 0 should be the temperature of sink. So in that case, the right answer is D, 0 Kelvin. The next question is, the efficiency of a Carnot engine is 0.4. If the temperature of the sink is 27 degree, what will be the temperature of source? We can calculate again from the same formula, eta equals to 1 minus T2 upon T1. We have to convert this in the absolute scale, that means 273 plus 27, and then we can calculate it, and the right answer will be 500 Kelvin, C option. The next question is, heat engine converts mechanical energy into work. B option, mechanical energy into kinetic energy, or heat into mechanical energy, or internal energy into work. What it do? We have seen the definition of heat engine. Any engine which converts heat into mechanical work is known as heat engine. So option C is the right answer for this question. The next question is, the efficiency of heat engine is always equal to 100%, equal to 0, more than 100%, or less than 100%. Again, recall the formula for efficiency. It is 1 minus T2 upon T1, and we know that the engine works only when T1 is greater than T2. That means T2 upon T1 is a finite quantity. That means eta will be equals to less than 1. So the efficiency will always be less than 100%, and the right answer will be D. Okay. Next question is, the correct relation between the temperature of source T1 and sink T2 is, T1 should be equals to T2, T1 should be less than T2, T1 should be greater than T2, or T1 should be half T2. Which is the right answer? Absolute right answer is the option C, where T1 should be greater than T2. Okay. The next question is, the work done in an adiabatic expansion of an ideal gas is given by W equals to P1 V1 minus P2 V2 upon 1 minus gamma, or P1 Y1 minus P2 V2 upon gamma minus 1. C option is W equals to R T2 minus T1, or option D is W equals to R T1 log V2 upon V1. So remember, adiabatic expansion was the second process of the Carnot cycle, and we have used the adiabatic expansion expression for a gas, where it was PV to the power gamma equals to constant, and finally we had calculated W equals to P1 V1 minus P2 V2 upon gamma minus 1. So the right answer is option B. The next question is, the efficiency of reversible engine working between temperature T1 and T2, where T1 is greater than T2, is equal to T2 upon T1, T1 upon T2. This is the formula for efficiency actually. So you can directly answer that the option C is the right answer, 1 minus T2 upon T1. The final question of today's quiz is the net work in Carnot cycle is given by W equals to P1 V1 minus P2 V2 upon 1 minus gamma. Option B is W equals to R into V1 minus V2 log of T2 upon T1. C option is W equals to P1 V1 minus P2 V2 upon gamma minus 1. Or option D is W equals to R into T1 minus T2 log V2 upon V1. So we have calculated at the end of our lecture that the right option is D, W equals to R into T1 minus T2 of into log V2 upon V1. So that's all for today's lecture. We have seen how the Carnot engine works, what is the meaning of reversible and irreversible process, what are the conditions for that, and we have solved some quiz also in today's lecture. I hope everything is clear for you all, and if you have any question, you can ask me by commenting in this video. Okay, thank you for your patience, thank you for your attention.